we're happy to see everybody online. And in the name of all of the organizers, Ankit is here. We have Krishna, he is in a seminar room at the University of Arizona. Seth is here. So we're very happy to welcome Professor Lepple to our material seminar this week. Professor Lepple is now a professor at the Justus Liebig Universität in Giessen, that is a university in Germany. And prior to her appointment, which has been quite recent, so only a couple of months ago, she started her professorship position there, so congratulations. She has been a junior research group leader at Decima, that's a research institute in Frankfurt in Germany, and she's done a postdoc at the Technische Universität Technical University in Darmstadt. She did her PhD at KIT in that's in Karlsruhe Technical Institute, I think. I don't know how to translate it, but it's in KIT is very well known research institute also in Germany. And we have actually met for the first time in Santa Barbara, I believe, if I try to remember which year that was, but it's been too many years ago, when she did some research with Carlos Levy at UCSB. And then later on, she also visited and had a research stay at UC Davis, actually working with Alex, Professor Nowrotsky, who is also here in the audience while she was still in Davis. And now Alex is here at ASU, and now Maren is visiting virtually at least. So we're very happy to have you here. Maren is a expert in the field of broadly ceramics, thermodynamics, and also CalFed. And Maren, the floor is all yours. We're excited for your talk.
Thank you, Christina, for the nice introduction, and sorry for the delays and my technical problems. So now you can see the slides. Can you also see, you see the full slides, right?
Yes.
Okay.
Yes.
Perfect. Okay, so as Christina mentioned, my research interests are in ceramics materials, especially ceramics for energy-related applications. And in this field, I do material development and based on thermodynamic considerations. So that's at least my title. And so now, okay, this works. So ceramic materials are used in a variety of energy conversion and storage applications, and here are just shown some example. I'm pretty sure that there are much more applications where ceramic materials are used, but for example in batteries, ceramic materials are used as electrode materials, especially the cathode materials, for example, in lithium-ion batteries, but also in all solid-state batteries, ceramic materials are used as solid electrolytes. In gas turbines, which can be used for propulsion in airplanes, as shown here in this graph, but also in land-based turbines for energy conversion, ceramic materials are used as protective coatings in the hottest parts of the engines. And in thermoelectrics, you can also find ceramics in fuel cells or electrolyzers. You can find ceramics, for example, as solid electrolytes, and also in concentrated solar power stations, ceramics are used. And the development of ceramic materials and also new ceramic materials led to several development leaps in the different techniques. And here I just showed the two examples for lithium-ion batteries or batteries in general and gas turbines. So with the introduction of lithium cobalt oxide and the introduction or the commercialization of lithium-ion batteries, the energy density for batteries made a huge jump and made all the small electric devices we nowadays use in our everyday life possible. And with the further development of this lithium cobalt oxide in the introduction of nickel and manganese into the structure, the energy density could be increased even further. For gas turbines, the process temperature could be increased with the introduction of ceramic materials as thermal barrier coatings, and they are applied in the hottest section on the metallic structural parts. And you see that there was a huge increase, and with further development of the TBC materials and the introduction of active cooling schemes, the process temperature could be even increased, and therefore the efficiency of gas turbines was increased as well. So to further increase the efficiency of these applications, new materials and new technologies are needed with high efficiency, low degradation, and at low cost, of course. So for materials development, as mentioned before, I usually use a thermodynamic approach, which can be summarized as in the Kalfat method. And here it looks maybe a little bit complicated, but that's more or less the flow chart of the Kalfat method. And in the Kalfat method, for every phase, stable and non-stable phase in the material system of interest, a model is chosen with adjustable parameters. So here in this box or in this equation, you can see an example for a stoichiometric compound or a pure element. And that's the function for the Gibbs energy with the adjustable parameters A, B, C, and so on. And now within the Kalfat method, these adjustable parameters are fitted to experimental data, for example, thermal analysis data, calorimetry data, phase diagram data, and so on. Or if they are not accessible experimentally, the data, then also estimates or theoretical data is used, for example, DFT or ab initio data. And then these adjustable parameters, A, B, C, and so on, are fitted to this data. Here I chose some examples. So A can be fitted to solution calorimetry data, for example. B, which stands more or less for the entropy, can be fitted to low temperature, CP data, or data which is gained from ab initio calculations. And the higher adjustable parameters can then be fitted to the heat capacity, for example. And if the thermodynamic optimization, meaning the adjustment of the parameters to experimental data, is done for each phase, for each model, then these data goes into a database, which is shown here. And this database is usually published and shared, and then users can calculate equilibria and phase diagrams, graphical representations, and for the applications they need. So the output are, of course, phase diagrams, but one also can calculate, for example, or derive synthesis temperatures, or identify the operating temperature limits. One can calculate driving forces for equilibrium and non-equilibrium phase formation, or one could, for example, if one is interested in batteries or electrochemistry, could calculate the open circuit voltage for the electrochemical reaction, for example. So I now want to give some examples, and I want to give the examples in the system or in the application for thermal barrier coatings. And as I mentioned before, thermal barrier coatings are used in gas turbines, either for the airplane propulsion or for land-based gas turbines for energy conversion. And they are applied in the hottest sections of the gas turbines. And here you can see, for example, an airfoil with the gas channels here, which are used for active cooling. And usually, so what you can see here in the bright phase is the superalloy, usually a nickel-based superalloy as shown here. And on this superalloy, a bond coat is applied, which provides good adhesion between the superalloy and the thermal barrier coating or the ceramic coating, and also provides some oxidation resistance because the bond coat forms a thermally grown oxide layer, which is alumina during the operation, which provides some protection against further oxidation. And then on this, the thermal barrier coating, so the ceramic material is applied, and it's usually a very porous structure, either lamellar or also just porous, and it has a very low thermal conductivity. And this graph you've seen before, so with time or over the years, the operating temperature increased. However, the specific core power with increasing gas temperature or operating temperature deviated even more from the ideal behavior here. And this is due to the active cooling, which is used to be able to obtain higher temperatures, but one loses some specific core power, and therefore new materials are needed which can either withstand higher temperatures or which have a lower thermal conductivity, or both in the best case, that one can go to higher temperatures without active cooling. The state-of-the-art material for thermal barrier coatings is yttria stabilized zirconia. So, and here you can see the phase diagram, starting from zirconia with increasing mole fraction of yttria. And yttria stabilized zirconia is used because it has a very good thermal cycling behavior, as you can see here with the red dots. And this is due to the formation of the metastable T prime phase. But this means that because we have a metastable phase, we have also a temperature limit for long-term operation of around 1200 degrees centigrade. If you go to higher temperatures, this metastable T prime phase will decompose to the equilibrium phases, which are the tetragonal and the fluoride phase. And so they are not favorable. So they do not have these good mechanical properties. And during cooling or during the thermal cycling, for example, the tetragonal phase will transform to the monoclinic phase. And this has a huge volume expansion. However, it's not so easy to find new materials because the new materials have to meet a lot of requirements concerning the properties. So besides having a long-term thermal stability above 1200 degrees centigrade, they have to have a low thermal conductivity, quite high coefficient of thermal expansion, so high for ceramic materials. They have to have a low sintering tendency, chemical compatibility with the alumina, so the thermally grown oxide, good corrosion resistance, and also good mechanical properties. And there are different strategies to find new materials. One is to co-dope the yttria stabilized zirconia with different elements. So maintain the zirconia-based material. Another approach is to go to new oxide materials. And the third one is to use non-oxidic or non-oxide ceramics. And these are the three approaches I want to discuss in the following. So when co-doping with yttria stabilized zirconia, the aim is, of course, to increase the phase stability, to make the metastable T prime phase, which is a tetragonal phase with a high tetragonality, stable up to temperatures above 1200 degrees centigrade. Furthermore, by adding additional atoms or additional elements, the thermal conductivity can be reduced because there's more scattering of the phonons. And also the mechanical properties can be improved, for example, by increasing the tetragonality as shown here by the elements cerium and titania. So I investigated the system Zirconia yttria tantala, which is also a very promising material system for the thermal barrier coating application, because in the zirconia-rich corner here, we have a very extended tetragonal phase field, which is stable to temperatures above 1500 degrees centigrade and stable to room temperature. It has a very low thermal conductivity and good mechanical properties. And this material system also has this yttria tantala phase down here, which also has very low thermal conductivity, good mechanical properties, and also thermal stability. However, for the whole system, there was lack of thermochemical or thermodynamic data, and especially for the yttria tantala phase field here, there were uncertainties about the phase stability. And yeah, so there's even for the binary phases like the yttria tantala system, or I think now there is a thermodynamic database available, but for example, for the zirconia tantala system, there's even no thermodynamic database available. And for the pseudo ternary phase diagram, there's no thermodynamic database available. So the goal of the project was to investigate primarily this zirconia yttria tantalate quasi-binary system and to get thermodynamic data. So when we look at the flowchart of the Calvert method again, in this project I will come to this in a minute, investigated the upper part. So we did a lot of experimental parts experiments, and I also started the modeling, so the thermodynamic optimization, and I'm now collaborating with Olga Fabrichnaya from TU Freiberg, who is an expert in the thermodynamic optimization. And the experiments I'm showing now were done in collaboration with Alex Nafrotsky and Kristina Lilova and Sergei Ushakov, at that time at UC Davis, but now they are all at Arizona State University, and also in collaboration with Carlos Levy and Chandra Mikoli from UC Santa Barbara. So concerning the phase stability of the yttria tantalate phase, there were some uncertainties in the literature. So 3 different structures were reported in literature. At room temperature, 2 monoclinic phases were reported to be stable. One was the M' phase and one was the M phase. And at high temperatures, the tetragonal phase is stable. And the thing was that, as you can also see here, when we were starting from the M' phase and heating the M' phase, for example, in a differential thermal analysis, we had one peak, so the phase transformation here to the tetragonal phase. However, on cooling, the tetragonal phase will not transform back to the M' phase, but will form the M phase. And then when you heat again, you will not see any signal anymore, because this M to T transition is a second order transition. So this was already reported in literature, and we found the same when we did thermal analysis in UC Davis. So maybe naive Maren thought, oh, well, we can find very easy, or we can investigate the stability very easy if we do just measure the enthalpies of formation at room temperatures, and then we can determine which of these 2 monoclinic phases is stable. So in Davis, or now in Arizona at ASU, so-called solution calorimeters are available or situated. So this means you have a very big calorimeter with two calorimeter chambers in which you have a solution, in this case sodium molybdate, and then we dropped the yttrium tantalate and yttrium oxide and tantalum oxide into the calorimeters and got the enthalpies of the solution. And with the thermodynamic cycle, we were then able to derive the enthalpies of formation at room temperatures of M prime and M yttrium tantalate. However, the data was more or less exactly the same for M prime and M within experimental uncertainty. So we couldn't say anything from this data about which of these two phases is the real thermodynamic stable phase at room temperatures. So we came up with the idea to do some heat treatments, and we started with a sample with M prime and heat treated it for 2 hours at 1500 degrees centigrade, where we were sure that the M prime would transform to the tetragonal phase, and then cooled it and heat treated it another 2 hours at 1210 degrees centigrade. And when we then investigated or did XRD, we saw that the M prime phase transformed to the M phase. Then we did the same heat treatment, so 1500 degrees C and 1200 degrees C. And this heat treatment, so then we obtained M phase and heat treated it again for 100 hours at 1400 degrees C. And then we saw, wow, the M phase transformed to the M prime phase. If we just heat treated the M prime phase for 100 hours at 1400 degrees C, we also saw the M prime phase stayed M prime phase. And from these experiments, we then concluded that M prime must be the stable low temperature phase. However, there's very little difference in the energy between M prime and M, and therefore the driving force is very low. So now you may wonder why this is even important. It's important because if yttrium tantalate is used as TBC materials, it might be M phase after the processing, so after thermal spray. But then during service, when you heat treat it for a very long time at higher temperature, it may transform to M prime during operation. And M prime has slightly different properties than M. And then such information is very crucial. As mentioned before, we did these enthalpies of formation measurements using solution calorimetry. Here you can see the instrument again. And we didn't do this only for yttrium tantalate, but also for several compositions along this quasi-binary from the zirconia to the yttrium tantalate, because enthalpy of formation data, as I mentioned before, is really important data when it comes to the thermodynamic optimization, because the parameter A can be fitted to this data. And so we obtained here the data for these compositions. So in the yttrium tantalate phase, in the tetragonal zirconia solid solution, and in the monoclinic solid solution. And here there's a huge difference between the values. So for the yttrium tantalate compositions, we found that the enthalpy of formation is quite negative, which means that we have a significant energetic stability, and we think it's because of the ordered structure of the yttrium tantalate. However, for the zirconia-rich compositions here, there is almost no non-energetic stabilization, and we think these compositions are stable because of the configurational entropy. So when it comes to high temperature materials and you want to investigate the phase transitions, then you might encounter some difficulties because there are not so many experimental equipment available where you can go to high temperatures. And yeah, so in UC Davis, or now in Arizona State University, there is a differential thermal analysis device which can go to 2,400 degrees centigrade roughly, and we use this to investigate the fusion of the yttrium tantalate. So in this case, Sergey welded the yttrium tantalate into a tungsten crucible and heated it to, I think it was 2,200 degrees centigrade. And here's the results, what we got. So the first heating curve, and then the second and the third heating. And what you can see is that the area under the curve, which gives the enthalpy of fusion, changes from the first to the second to the third heating cycle. And first we were thinking that maybe the sample would react with the tungsten or would like creep up the crucible. But when we did post experimental analysis, we saw that the sample most likely reduced in the inert atmosphere at the high temperatures, because we saw several phases, so the sample was not phase pure anymore. However, when we took just the first heating, the first melting event, so we did several measurements, taking new powders every time, or new samples every time, we got a value, but this value had a quite high uncertainty. So we decided to use another technique, which was invented by the group of Alex Navrotsky and Sergey, which is called a drop and catch calorimeter, as you can show here. I can see here. So in this case, a spherical sample is levitated in a gas stream and heated by a CO2 laser, and the temperature is recorded by a pyrometer. And then the hot sample is dropped, also the levitator is opened, and the hot sample is dropped into a calorimeter, which is kept at constant temperatures of 25 degrees centigrade. And then what you do is plotting the enthalpy increment from the sample temperature to the calorimeter temperature. And this is the data, like all the black dots here. And then from the difference of the molten samples, which were caught in the calorimeter, and the solid samples, which were caught in the calorimeter, you can then derive the fusion enthalpy, which was actually quite close to the enthalpy measured by differential thermal analysis. However, the measurement uncertainty was much lower. And all this data, which I've shown here, is invaluable for the thermodynamic assessment and for further development of new TPC materials. And we are now extending the whole system to the quaternary system, zirconia oxide, hafnium oxide, yttrium oxide, and tantalum oxide, in collaboration with Olga Fabrichnaya. And we want to then develop the thermodynamic database. So, as I mentioned before, one can also try to find new materials, new TPC materials in other oxide ceramics. And a quite new class are the multi-component equiatomic oxides, or the so-called high entropy oxides, which are shown here. They are complex single-phase oxides with 5 or more metal cations in equiatomic proportions in one or more of the cationic sublattices. So here it's shown for lanthanum circonate, where the lanthanum is replaced by 5 rare earth elements, and therefore the configurational entropy, at least in theory, is increased. If it's really true that configurational entropy is increased, and if the compositions are entropy stabilized, has to be proven. But Well, that's at least the concept. And for high temperature materials, the high entropy oxides are very interesting because according to the Gibbs-Helmholtz equation, the entropy term becomes more important with increasing temperature, and so the phases are stabilized at high temperatures. And another thing is really important because usually if one does materials development, one is usually in one corner of material system. But now, since we use equiatomic proportion of each element or each cation, we move to the center of a material system. And so the hope is to find new composition with extraordinary properties within these compositions. So in the project, which is funded by the BMBF, we decided to investigate high entropy rare earth zirconates. And besides the improved high temperature stability, we think that due to the lattice distortion effect and the increased phonon scattering, we will obtain materials with low thermal conductivity. The high entropy oxides will also have low sintering tendency because of the sluggish diffusion effect. And we have a high variability in compositions, so the properties can be designed to the needs. And this is the example I showed before, where we, for example, in lanthanum zirconate, replace the lanthanum by 5 elements. And it has been shown in literature before that these high entropy zirconates are promising because they have a lower thermal conductivity and a quite fitting thermal expansion coefficient. So in terms of the Calvert method, when we look at the flowchart again, for this project, we used existing data for the binary systems to calculate or to derive another phase diagram, which we used to determine the compositions we wanted to synthesize. So we synthesized in total, this is the new phase diagram, which gives the temperature independence of the cation radius ratio, because in the pure or in the zirconate with this chemical formula, the cation radius ratio of A to B determines whether the composition crystallizes in the defect fluoride structure or in the pyrochlore structure. And we derived this phase diagram to see in which structure the binary oxides would crystallize, and we wanted to see if the high entropy oxides also follow this rule. And we synthesized 10 high entropy oxides with systematic variation of the cation A according to the size and the mass. And here you can see the elements which we used. So that's, I mentioned already that this was one of the goals. And the other one was if we could find a general rule to predict phase pure materials. And then what we are still doing is to find out the influence of the composition on the properties. So these are the 10 samples, and we found that 5 samples were single phase, 4 of them were pyrochlore structure, and 1 of them was fluoride structure. 3 samples did or had multiple phases, and the 2 samples down here, they did not incorporate all the cations we wanted to incorporate, so I will not talk about these compositions. But here you can see the samples in this phase diagram, and it was actually true that the one sample forming the defect fluoride structure had a quite low cationic radius ratio, whereas all the other samples which crystallized in the pyrochlore structure had a cationic radius ratio of 1.46 or higher. And then we had two samples which had two phases or which showed two phases, and these two phases were then also crystallizing in the defect fluoride or pyrochlore structure following this cationic radius ratio. And now it would be interesting if also these phase pure samples, for example, this sample here, sample 2 and sample 4 had a cationic radius ratio of 1.46, if they also would transform, for example, here slightly above 1500 degrees centigrade from the pyrochlore to the defect fluoride structure. But this is some experiments we still want to do or need to do. So the other thing was we wanted to know why these these two samples were actually multi-phase samples. And we found that the atomic size difference delta, so here's the equation for that, is a quite good value to determine whether a single phase forms or not. So here are actually the compositions of the different samples. And here you can see the atomic size difference delta, and we found that the threshold value is 4.5%. And we benchmarked this value to other compositions which were published in literature. And our result is in accordance to the previous reported data in literature. So now the next step would be to determine also the other properties which are relevant for thermal barrier coatings, independence of the compositions, and to increase the number of cations on the A side, but also synthesize compositions with additional cations on the B side, so on the zirconia side. Okay, so the last approach is to use non-oxide ceramics for the thermal barrier coating application. And in a research training group from the German Science Foundation, we investigate polymer-derived ceramics. And the research training group is actually where we want to find or want to investigate a completely new material system. So starting from the metallic substrate to the bond coat, and then find a new top coat. And this is a joint project with the KIT, the Technical University of Darmstadt, and the Decima Research Institute. And we are actually investigating the oxidation behavior of polymer-derived ceramics as a function of the composition and the microstructure. And the goal is to use these findings to help with the development of an oxidation-resistant ceramic coating system. So we are actually just looking at the top coat at the moment. And in this project, we used CalFAT. We used an existing database to calculate the oxidation reaction of different starting phases. And this helped a lot with interpreting or with the interpretation of our experimental findings. This thing with silicon-based ceramics is that they behave very well in dry oxidizing atmospheres. So the silicon-based ceramics form as a thermally grown silica oxide scale. which is resistant and which provides good protection against further oxidation. So if you look here at the oxidation kinetics, we follow this parabolic kinetics, which is very advantageous. However, if you go to combustion atmosphere, they contain water, and the water vapor reacts with the oxide scale, with the silica oxide scale, forming silicon hydroxide, for example. So in this atmosphere, you have a simultaneous silicon oxidation with evaporation. And then you end up, so you in the have the parabolic silicon oxide formation and the silicon hydroxide evaporation, which is linear. Then you end up with such a paralinear behavior, and in the end you lose your material and your coating. So in a first shot, we investigated actually composite materials with zirconium boride as filler material and silicon carbonitride with zirconia and boron as filler, as matrix material. And zirconia boride was used because it's a very well-known ultra-high temperature ceramic, but it has low oxidation resistance at temperatures above 1000 degrees centigrade and a sluggish sintering behavior, so processing is not that easy. And it has been reported in literature before that, for example, using silicon carbide improves the sintering and also the oxidation behaviors. And we, instead of silicon carbide, we used the polymer-derived ceramics as sintering aid, and this was actually done with Emanuel Ionesco and Ralf Riedel from the Technical University of Darmstadt. So we had these different samples here, zirconium boride with silicon carbonitride, and then with zirconium and boron in it. And we used a thermal gravimetric analysis, EPMA, XRD, and Calfert to evaluate the data. We wanted to investigate the oxidation kinetics, the oxide scale, and propose an oxidation mechanism. So here's a schematic of a thermal gravimetric device. So we have a balance and we have the sample in the furnace, and on the other side we have the reference. And these are the kinetics we were expecting for the different starting phases which were in the sample. And what we obtained is this one shown here. So we had a quite good oxidation behavior, which were almost parabolic, but with a little linear proportions. And the samples behaved a little bit better than the zirconium boride with pure silicon carbide. And the best behavior was for the polymer-derived ceramic, for the silicon carbonitride without zirconia and without boron. And after oxidation, we did the microstructural analysis, which is shown here. So the cross section, and we had on the sample, we had a class C silicon oxide scale. And we also had several of these bubbles here. And these bubbles could also be seen in the microscope from the surface. So here are the bubbles in the secondary electron microscope image. And if we had the backscattered electron microscope image, we could really see that below these bubbles, we had a lot of zirconia. So we also did EPMA on the cross section, and there we also saw that below the class C oxide scale, so in both cases, we had zirconia oxide, a very thin zirconia oxide layer, which is shown here, and then we had actually a silicon depletion. So, and of course these bubbles. And then we used a thermodynamic database from one of the PhD students of Hans Seifert from KIT. to calculate the oxidation or the stability of the starting phases independence of the oxygen activity. And this, as you can see here, zirconium carbide or zirconium nitride or zirconium carbonitride decomposed with increasing oxygen activity to zirconia, forming carbon monoxide, nitrogen and carbon dioxide. Zirconium boride forms zirconia and borea, and silicon carbide forms CO or carbon monoxide and later carbon dioxide. But yeah, so this didn't really explain why we saw this silicon depletion zone. And for this, we had to go a little bit more into detail as shown here. So the oxidation of silicon carbide. And what you can see here is that at a certain activity of oxygen, silicon carbide decomposes into silicon monoxide, and silicon monoxide is gaseous, so it also wants to leave the sample and goes to the edges. And as you can see here, so if you have, this is the sample, then the oxygen partial pressure or the activity of oxygen increases when you go from the middle of the sample, so from the bulk to the edges. So here the silicon carbide is stable, then it forms silicon monoxide, which wants to leave the sample. And then at some point, the oxygen partial pressure is high enough that the silicon monoxide forms or is oxidized to silicon dioxide, which is stable again. And then you have the zirconia and the silicon oxygen boron and the Classy scale here. Yeah. So now I come to the end of my talk, and I hope I could show you the different, or introduce you to different approaches to develop new TBC materials. And I hope I could show you that thermodynamic experiments and calculations are a very useful tool for materials development and for interpreting experiments, and yeah, also for application. The Kalfat method is a very useful tool. And with this, I want to thank all my different collaborators at the Dekima Research Institute, at Arizona State University, Theo Berger Akademie Freiberg, University of California, Santa Barbara, the Technical University of Darmstadt, and the Karlsruhe Institute of Technology. And I want to thank you for your kind attention.
Thank you, Maren. Virtual applause. I know that Seth has some questions for you. So Seth, if you don't mind to just unmute yourself and ask the questions.
Absolutely. Maren, thank you so much for this beautiful talk. My questions are more clarification questions. Can we go back to slide 29 if possible? You talked about silicon depletion layer forming.
Yeah.
So do you know if anybody tried to create this enclosed chamber design where you would place extra silicon chips to create this high silicon vapor pressure to avoid the silicon depletion? Are you aware of any of that kind of work? Is this possible?
Actually, I don't know.
Okay.
So in this case, we didn't try because we wanted to, or yeah, we didn't even think about it because we wanted to be as close to,
okay,
the application as possible. And so after these oxidation tests were not really that promising, we didn't even try the wet conditions.
I understand. That's fair enough. In semiconducting industry, if we want to really avoid the silicon depletion, it could be any kind of silicon carbide, silicon nitrides, anything. you can imagine, usually the chambers involve these extra silicon chips. Quite literally, people just place a few chips there. At high temperatures, it creates this high silicon vapor pressure and prevents the diffusion or vacancy creation to be possible. So I was just wondering if it's a possibility at all. The last clarification question will be on slide 25. If we could go back to that slide if possible. So right here, you have shown this beautiful mass change versus time graph in hours. And it's very clear it is quadratic, but there's a deviation in the later stage. So I would say probably 20 hours and onwards. Is this because you have this depletion layer the diffusion layer forming? I didn't quite catch what kind of sample we were looking at. Is it microstructured? Is it palletized? What is the reason for this deviation basically in the later stages?
It's a pallet. And I think we have several things going on. We do not only have the parabolic oxidation, but we also have linear mass loss because, for example, the borea, which should be liquid, but it also evaporates at these temperatures slowly. And there are also other oxidation reactions going on, which have some linear portions. And so we actually calculated the kinetics, and we found different linear portions to it, but it was really difficult to derive which reaction accounts to which kinetic.
So basically, there are many reactions taking place. Many of them are quadratic, but when we superimpose on each other, maybe perhaps it comes across as what you're observing in 24 hours and onwards, together with the mass loss. Is that correct?
Yeah.
And
we did not have enough samples to redo or to do even longer experiments.
And which element was missing for the most part during the reactions? Which element were you missing?
Like which element?
Can you remind me which one was that? Okay.
So we had the zirconia carbonitrate, and then we had with zirconia and boron. And yeah, I mean, in the end, if you think about it, if you have zirconium in, or it's the same for zirconium boride, or if you have zirconium in there and you oxidize it, you will form zirconia, and at higher temperatures, zirconia is an ionic conductor. So,
but you have a mass loss during this reaction. Which element is missing during the reaction? Can you remind me that, if possible? Boron is missing.
For example, the boron, the liquid, will evaporate at these temperatures.
Okay, and what was the temperature roughly?
1300 degrees centigrade.
1300. Okay, very good. I'm good with the questions. Thank you.
All right, thanks, Seth. Peter, you have a question.
Maren, thanks for the nice talk. I just was the high entropy oxide part. When you were talking about the fluorite structure, for the pyrochlorite, I understand the A and the B site. In the fluorite structure, are there two different Wyckoff sites for the cation? So how do you, so when you talk about an A and a B site for the fluorite, how are they, is that just an arbitrary, I didn't quite catch what that meant, I guess.
So we actually start from this chemical formula. So we
that's the pyrochlor, right?
The pyrochlor, and B is zirconia, and then we added this, and it's known from the quasi-binary oxides or pyrochlors that if the Ra to Rb ratio is small, then you will have the defect fluoride structure. And then you do not have different Wyckoff positions for
so the sort of oxygen vacancy that you might, if you were thinking of the pyrochlor and the fluorite, the oxygen vacancy gets filled in then when you substitute for the high entropy alloy. So I see. So it goes to 08 rather than 07. But But you start from pyrochlore and you exchange the A then, is that correct?
Yeah, we exchanged the A, but we no, we kept it constant to 7. So this is a trivalent cation. And so we also used trivalent cations, and for the samples 9 and 10, we tried to add a divalent and a tetravalent cation, but this did not work. So we, for example, used magnesia and zirconia, and then we formed some magnesium oxide.
So there's always, in the high entropy oxides then, or in this class, there's always like a kind of an oxygen vacancy relative to the fluorite structure then, is that right? It's always 07 when you make them?
Yeah.
I see. Okay, thanks. Interesting.
Okay, Sandhya, do you want to ask your question yourself?
Yes. Hey, Maren, nice talk. So I was wondering about how do you categorize the ordering in these high entropy alloys? Is there a typical grain size you expect wherein you call them high entropy versus them being just polycrystalline materials? Or I was just curious about the parameters that you think of when you are talking about high entropy alloys.
Yeah, so, well, I, as a thermodynamic person, I actually don't really like to call them high entropy oxides, because I'm really not sure if they're high entropy or if they are entropy stabilized. But it's more catchy and more easy than talking about multi-component equiatomic oxides. So that's why I call them high entropy oxides. And so I don't know if I got the question correct, but for me, the high entropy oxides are actually the oxide, or the multi-component equiatomic oxides are the ones which form a single phase oxide. I think it's a little bit similar to the discussions also for the high entropy alloys and the complex. I don't know, they have all the different names, and compositionally complex alloys and so on. And usually there you do not really have one phase, but for the oxidic or for high entropy ceramic materials or multi-component equiatomic ceramic materials, you can much easier obtain a single phase material than for the metallic alloy system. At least that's what I feel. And I don't know if I really answered your question, but maybe you can ask again.
I also don't know. I'm pretty new to this field, so I just was curious about the terminologies and how do we define things here. So
yeah, so there's a lot of different definitions also in literature. I think the ceramic community learned a little bit from the metallic high entropy alloys community, trying to define it a little bit better. But of course, since it's a quite new topic and everyone wants to be catchy, a lot of people just call it high entropy oxides or ceramics, and don't prove if it's really with high entropy or entropy stabilized.
Maren, maybe since we're talking about the high entropy topic, for just in your group, as a standard, let's say, procedure operation, how do you go about saying, yes, this is actually a single phase with like 5 different elements, whatever, in a certain structure? Do you do long measurements with the X-ray diffractometer, or do you want to see on top of that at least some, EDX measurements? How do you do that? What do you expect of your students to prove to you it's actually a high entropy alloy, or whatever we call it?
Yeah, so we do quite long heat treatments at high temperatures. So for example, 100 hours at 1500 degrees centigrade. to be sure that we reach equilibrium, because we've seen before that, for example, the composition at first looked like it would be single phase fluoride structure, and then after a longer heat treatment, it turned out it was dual phase with the defect fluoride and the pyrochlore structure. So I think if you have a new composition, it's quite important that you also do long heat treatments at quite high temperatures. And then we do XRD, SEM with EDX and EPMA. And then, yeah, I think that's for if you do the long heat treatments, then and you have phase separation, then you should see it in one of these techniques at least.
Okay.
So
Thank you.
all of that tells you about long range order that you catch an X-ray, but certainly our experience with pyrochlorous and perhaps with defect fluorides as well is that there are all sorts of funny short range order things going on, which would stabilize the energy and diminish the entropy. So I'm not sure that quote unquote high entropy oxides are any higher entropy than high entropy alloys. It's a matter of the scale of short range ordering.
Yeah, I agree. I totally agree.
Mukesh, can you, I see a raised hand. Can you unmute yourself?
Thank you, Maren, for nice presentation. And I have just a follow-up question for my clarification on slide 25. So you conducted TGA measurement at 1300 degrees centigrade. So I'm just curious to know that whether this material was stable during the ramping of temperature.
Yeah, so from the polymer-derived ceramics, it is known that it has some free carbon, which burns during the heating. But so yeah, so we burned this for all the samples and then it was stable.
So how much the weight percentage loss during the ramping process or achieving the 1300 degrees centigrade?
Actually, I'm sorry, I don't know. I cannot answer these questions at the moment. I would have to look into the data.
Okay, thank you.
Okay, are there other questions for Maren at this point?
So just a comment, Maren, all our calorimeters are up and running fine. So if there are things that you need to do with us that you can't do in Germany, let us know.
Thank you. Yeah, I'd be really happy to further collaborate and work with you and hopefully stop by it and visit at some point.
Yep, we are open and running and everybody's fine.
Perfectly.
Yeah, thank you, Maren, for the great talk. Good we didn't lose you to industry. Yeah, I was wondering why non-oxide coatings are even considered for TBC for long lifetimes. I would guess they wouldn't live long at 1700 C in air, no matter what. Can you comment on that? Yeah,
actually, it's more an environmental barrier coating than a thermal barrier coating. So the structural material, the metallic material, which should be, which we consider in this consortium is a MoCT. So, and yeah, molybdenum and yeah, might evaporate. So actually, the polymer-derived ceramics should work as an environmental barrier coating, and usually so rare earth silicates are already used, for example, for CMCs as environmental barrier coating. And so what we are thinking now is that we actually have several layers. So we have the metallic layer and the bond coat, and then we would have the polymer-derived ceramic as the environmental barrier coating. And on top of that, we will have an additional thermal barrier coating. So yeah, I don't believe that these polymer-derived ceramics or silicon-based ceramics or non-oxide ceramics will work as thermal barrier coating themselves. Yeah.
No, thank you.
Okay. It is shortly after 9 p.m. in Germany. So Maren, we should let you finish out your evening, maybe with a glass of wine. Thank you so much for joining us. That was a fantastic talk. And yeah, I will be in Germany actually in a week. So we should definitely figure out a way to see each other. Yes, perfect. Okay. Thank you so much. Thank you
for hosting me.
Everybody. Thank you everybody for coming. And I wish everyone who has still their workday ahead of them a good Friday and have a fantastic weekend. And we will have our next materials seminar next Friday. Goodbye, everybody.
Bye.
Bye, Maren.
Bye.